So in the last lecture, we had some Bell inequalities, the CHSH inequality, and we saw how it works. We saw it's violated in quantum theory and discussed the background a little bit. This lecture will go deeper into the theory of Bell inequalities because CHSH is obviously not the only Bell inequality. There's way more. And here I'll give you some of the more advanced topics in the theory of Bell inequalities. So we'll mainly talk about the facet Bell inequalities, some loopholes in experiments, and the NPA hierarchy. But I'll try to make the NPA part understandable, but not very protracted. The main goal of that part would be to just give you first exposure of the NPA hierarchy, because it's one of these topics that people usually don't get the first time they see it. So this should be your first time dipping the toes in the water, and the next time you actually try to use it or try to understand it more, you will be already a little bit there. Did you do NPA before?
Not for my bachelor.
Ah, okay. So it's the theory of Bell inequalities. And we'll start with a nice lemma. And the lemma is that the set of these behaviors, P, A, B, given X, Y, so this is what we measure in the Bell experiment, that have LHV is a polytope. Is a polytope, which means it's a convex hull of finitely many points. The proof is almost straightforward because we just say that, okay, if this guy has a local hidden variable model, then by our definition, it's of this form. This is just the definition. Now, this P of lambda is a probability distribution, so we are doing a convex combination of these kind of product points, which means that the extreme points of that set must be of exactly somehow this form. So we have just convex combinations of these. And okay, so let us look closely at the behaviors that just look like that. So you can see this as a sum of exactly one lambda. Now, what's this?
I think it was the probability that you measure X and A.
Otherwise around. The probability of A given X. Yeah. But now, which means that this PA given X must be always positive because, well, it's probability. And we must have that sum over A of PA given X is equal to 1 because given X, something must happen. But that means that we can construct a matrix P of A, which is nothing else than just matrix with entries P of A given X. Okay, so for example, for A and X being for 0 and 1, this would be the matrix that is P0 given 0, P0 given 1, P1 given 0, and P1 given 1. So this is example. Well, but this is nice because now this condition just means that if you sum the columns of the matrix, they must be normalized to 1. And this condition just means that all of the entries of the matrix are positive numbers. And this just means that PA is column stochastic matrix. Now, column stochastic matrix is nothing else than just a name for a matrix that obeys this and this condition. So this is a mathematical term, but it's good to know mathematical terms because if you want to know more about such matrices, this is what you need to Google and find in Wikipedia or find in some books. And one nice result about column stochastic matrices, which is the generalization of the Birkhoff-von Neumann theorem, is that PA is just always, as a column stochastic matrix, going to be convex combination of column stochastic matrices with entries with, which are 0 or 1. So it's going to be convex combination of column stochastic matrices with entries which just means that, for example, this is going to be 1 and 0, 0 and 1, or something like that. Now, of course, there's finitely many of such matrices because there's finitely many of elements in this matrix, so we have finitely many combinations of how to distribute these ones among the columns. So there's finitely many of these matrices, which means there's the matrices PA, they are in the convex hull of finitely many points. So when we go to these products, we just get convex combinations of finitely many points. Just take products of these column stochastic matrices that have entries that are zeros and ones. Okay, so in this way, we get the extreme points of the polytope of the behaviors that have local hidden variable model. Now, I want to give you an explicit example of this so that somehow you believe me it is actually so. And for that, we can just take the simplest non-trivial example, which is a column stochastic matrix, which is 2 by 2. Of course, A and B here are numbers in 0 and 1. And well, first of all, what we do is that we split this thing, so we can write this as so if you add these things together, you get exactly A here, 1 minus A here, the dot is for 0, and here you get A times B plus 1 minus A times B. And now you do the same thing for these columns, so you get something like AB 1, 1, 0, 0 plus A 1 minus B 1, 0, 0, 1 plus 1 minus A B 0, 1, 1, 0 plus 1 minus A 1 minus B 0, 0, 1, 1. And you can do the same thing for arbitrary bigger matrix. Now, this is important result because, first of all, this tells us that if we want to test whether something is a Bell inequality, so if you want to, so what is a Bell inequality? It's inequality that holds on everything that has local hidden variable model. Since it's a linear inequality, it's sufficient that it holds on the extreme points, okay? Because if I have inequality, so for example, if I know that some linear function, say for example, alpha x is less than a, and I know that alpha y is less than a, then I know that also alpha of some kind of px plus 1 minus py is less than a. So this is for numbers, but we can also do the same with vectors. And of course, we can represent all of these products of matrices as some kind of vectors because we can always unroll them into vectors if we would want to, or choose some kind of basis. So we just need to check whether any Bell inequality holds only on finitely many extreme points of the polytope of behaviors that have local hidden variable model. So in principle, if you want to check whether some inequality is a Bell inequality, or you want to take coefficients and find the biggest upper bound that you have, you just need to write a program that will iterate through all of these extreme points of the set that has local hidden variable models, and just always compute the number you have there, the highest possible bound that you get for your wannabe Bell inequality, and then you get some inequality that holds on the set of all behaviors that have local hidden variable model. Now the question is whether it's actually a useful Bell inequality in the sense whether there exists at least some non-local behavior, so something that doesn't have local hidden variable model that would violate it. To find that out, you would have to work harder because you would have to find an explicit violation, at least one of them, which you in principle cannot do in this way because this doesn't really tell you anything about the structure of those behaviors that do not have a local hidden variable model. But at least you can check that what is the highest bound on those. Moreover, this somehow enables us to tap into a big part of mathematics, that's the polytope theory and this kind of geometry and convex geometry, because there a lot of things are known, a lot of research was done, and we can basically just take all of this research, pick the stuff that's useful for us and apply it to our problem. So now I'm going to make a little side tour to polytope theory. Or theory of polytopes or convex geometry or whatever you want to call it. So as I said, polytope is just a convex body that's convex hull finitely many points. And this immediately leads us to answering a question of how do we write down what polytope we have in mind. Because we don't want to do an abstract theory of polytopes. We don't want to do abstract convex geometry. We have concrete polytopes that we want to investigate. Okay, so we are doing something more computational, and for that we need to exactly write down what polytope we have in mind. And so what's the first way to write down what polytope we have in mind from the definition?
I guess we have to pick out the points.
Yeah, just list the extreme points. I say that your polytope is convex hull of this. So that's what we call the V representation. And the V stands for vertex probably, because I think we would call the extreme points of polytopes vertices. And this is just by listing extreme points. So if I give you the list of extreme points, it's in principle not immediately obvious to determine whether a different point is in a polytope or not. Well, you can always say that I have extreme points, so I can, if it's inside, it can be expressed as convex combination of the extreme points. So I have like some kind of problem for finding these coefficients p lambda of the convex combination, and that would be a linear program. So that's one way to determine if you have a behavior, whether it has local hidden variable model or not. Just list of all of the extreme points, and now solve a linear programming problem for these p lambda. And linear programming problem is something like semi-definite programming problem, but actually easier and runs way faster. But now the different way to describe polytopes is something that's called the age representation. So the age representation and this is just to express polytope as intersection of hull spaces. So what's a half space? It just tells you that you just make a plane and say that half space is everything on this side of the plane. Since n-1 dimensional planes corresponds to some kind of normal vectors, we can express this as an inequality, which means that half spaces are one-to-one to their normal vectors and thus to linear inequalities. Of the form sum over I, AI, xi is less than b, where now these are the coefficients of the normal vector or of the inequality, and also this b, this bound, is the coefficient of the inequality. This x is the vector that we are plugging into the inequality. Is that clear? It's already starting to become obvious why I'm telling this to you. Okay. So now, given age So given the V representation, we can list the extreme points, but we can also list additional points. So for example, if I would have polytope which looks like this, it has clearly 4 extreme points, but I can also give you additional point inside, and I can say there is a convex hull of points x1, 2, 3, 4, 5. So somehow I'm giving you additional point which is not really helping you. So we say that the V representation is minimal if it lists exactly the extreme points. Now in this case, the H representation would list these half spaces and somehow the directions, it's over there, over there, over there, and over there, and you can see that the polytope is intersection of all of those half spaces. So a point in the polytope is the only point that lives on the left side of this half space, top side of this one, right side of this one, and bottom side of this one. And that's the whole polytope. Thus, we also can have a minimal H representation because I can also give you additional half space here and say like on this side of that half space. But again, this is not telling you much. So we have minimal H representation. Which is unique because it's the minimal one. It's the one that lists as few half spaces as possible. And this one is unique and lists facet inequalities. So now I have to explain this word facet. For a 2D polytope, the facets are exactly these edges. For a 3D polytope, the facets are the two-dimensional faces of the polytope, so the two-dimensional sides, like when you have a cube, it has 6 sides. For n-dimensional polytope, the facets are the n-1-dimensional faces or sides of the polytope. Of course, every polytope is somehow surrounded, or the boundary is completely given by listing all of the sides it has, so all of the facets. Okay, so now we can go to the polytope of LHV models. So this is the polytope of all of the behaviors that do have local hidden variable model. And we know that the vertex representation is given via these types of column stochastic matrices that have entries in 0 and 1. So this is using column stochastic matrices C lemma. Now, the H representation, so what would be in the H representation of the polytope of behaviors that have local hidden variable model?
Intuitively, it feels like it should be sort of the Bell inequality.
So, I would say facet Bell inequalities. Because obviously some Bell inequalities do not have to correspond to facets of the polytope, some do. And in principle, we want the facet one because those are the ones that we want to look for. And what else is going to be there? Yeah?
The constraints like positivity and summing to them.
Exactly. Now, we already live in the vector space where so the way we defined it, we already live in the vector space that would be tensor product of column stochastic matrices. So the summing to 1 is always enforced, but we still need to enforce the positivities. So what we get is that the H representation will consist of these trivial constraints and of these Bell inequalities. And we also have these PA, B, X, Y is A prime, B, A prime, B, X prime, Y. But somehow we have taken care of this by already jumping into the subspace of column stochastic matrices or tensor products of those where this is always enforced. Okay, now what happens if I drop the Bell inequalities and I just keep this thing and that thing? I still get a polytope, but what is this going to be the polytope of? This is going to be the polytope of all non-signaling behaviors. So if you take just the positivity constraints and the normalization, which we can somehow impose by definition, because those are linear constraints. You get the polytope of non-signaling behaviors, and you can immediately write down its age representation. If you also add the Bell inequalities, you get the age representation of the polytope of those things that have local hidden variable model. This shows that for LHV polytope, so for this polytope of behaviors that have local hidden variable models, we know V representation, but we want the age representation. For the non-signaling polytope containing all possible behaviors, including PR boxes, we know the age representation, and we would like to know the V representation. But that's, I would say, a little bit less of a burning problem, because it gives you also those non-signaling behaviors that are outside of quantum theory. So the problem of knowing V representation and trying to find age representation is known as the polytope inversion problem. And this is computationally not so easy to solve. So in principle, we can say that we have a solved scenario if we use either our wits or computers and a large amount of computation time to find the age representation of the polytope of behaviors that have local hidden variable model. And this was actually done for some of the simplest cases. So for example, we know that if Alice and Bob have 2 inputs and 2 outputs each, so 2 measurements with 2 outcomes each, then the age representation is known because it contains the positivity constraints, and all of the Bell inequalities are just CHSH inequalities. There's 8 of them because you have 4 positions of the sign and you have upper bound, lower bound. For more complicated scenarios, there's more than just one class of Bell inequalities. So there's going to be, I don't know, say, for example, for Alice, Bob, and Charlie, each having 2 measurements with 2 outcomes, you get something like 42 maybe classes of constraints, which one of them is this one. Then you get some CHSH inequalities on 2 parties, and then you get some tripartite things and so on. So, you know, it grows way more. And these are just classes of constraints. So this is like seeing CHSH as just one class, because you can obtain everything by some local transformations. But anyways, if we are doing something simple, we can always try to look up the list of solved scenarios, which is, for example, listed on the websites called Facets. And there you can find those ones that are solved. If you're doing something beyond this, you have to scour the archive and the internet for known Bell inequalities. Also, if you have a Bell inequality, it's not impossible to check that it's a facet Bell inequality, because all you need to do is list all of the extreme points of the LHV polytope and just check whether the inequality is somehow saturated on an n-1 dimensional face of that, which is like doable on a computer. You can figure it out if you really want to. Okay, and there was actually a lot of research into this, and at some point people stopped looking for more age representation because it just would take more and more computational time, and there are some methods to go like to really high scenarios, but then you usually don't get the full age representation, you just get some facet inequalities, and we know that the list is incomplete, but it's probably better than nothing. So the next thing that we have to discuss are loopholes in Bell-type experiments. Have you heard about this before? So what this does is that it looks at all of the hidden assumptions that we used when deriving the CHSH, the violation of a CHSH inequality and other Bell inequalities, and tests whether they are actually satisfied in an experiment. So loophole is going to be some operation that, if performed, can lead to violation of Bell inequalities even with local realistic theory. So we'll write down some kind of local hidden variable model and say that if we can do this operation, then we can actually violate CHSH even without using quantum theory. And thus, if we want to have a realistic loophole-free Bell experiment, we have to somehow make sure that all of these loopholes are eliminated as well as possible. This was in principle done in 2015, which was the, I think 2015, the loophole-free violation of CHSH in Austria. in Vienna, I think. Okay, so the first loophole that we are going to look at, and of course I would say that there's various ways to describe these loopholes. Not all of them are completely different from each other, and I'm just going to give you the two ones I consider the main ones, but you know, it's different people have slightly different names for them and describe them slightly differently. So sometimes you can see that, oh, what this person is talking about can be actually seen as instance of that loophole if we transform it in this way and so on. So we're quite certain we know all of them, but there's like, I don't think there's like a unique list that everybody would agree that this is how we should list them. You know, it's always a little bit messy. Okay, anyways, the first one that we should talk about is the locality loophole. And the question is that, are measurements really local operations? Or can the measurement device know the setting of the other device? Of course, it's hard to ask, like, how would Alice's measurement know the setting of Bob's measurement? But if I would set the measurement settings today and perform the experiment tomorrow, which is probably not unheard of in experiments, because to set the measurement setting, you have to probably rotate some, you know, polarization plates or whatever, and tighten some screws and polish some mirrors. And it's completely reasonable to prepare everything today and measure it tomorrow or next week or whatever after your advisor checks it or something like that. But in principle, since you're waiting between setting and measuring, somehow the information could spread. We don't know how, but it could spread, like nature could know, because the information could maybe because you rotate the mirror, this, you know, disturb some kind of hidden field ether that we don't know of, and this propagates the information to the other side, or something like that. So, so can Bob's measurement know Alice's settings? Well, and now we have two things to do. The first one is that we have to show that this is actually a problem. And this we're going to do by demonstrating explicit example that if Bob's measurement device can know the setting of Alice, then we can write down something that looks like a local hidden variable model, but actually maximally violates the CHSH inequality, which is somewhat of an overkill, but shows you that this would be a very problematic case. And the second thing is that we have to discuss solutions, like how to get rid of this kind of problem. So we start with the example. And in this case, we will have that the behavior at our hand is going to be given by the particles agreeing on some kind of hidden variable and sampling from it. And now on Alice's side, it's all the same thing that we have before in local hidden variable models. So we just have the correct response function. But now Bob's measurement outcome can also depend on Alice's setting, okay? So we assume that Bob's measurement device knows the setting of Alice, so it knows X, which means B can depend on X. So we put X here as a condition. So, okay, now we choose lambda from the interval 0, 1, P lambda to be 1/2, and PA given X lambda to be delta A lambda. So what this means is that Alice's measurement device does not even look at the value of X. It always returns lambda, or it always returns A equals lambda. Or in other words, what this means is that you have probability 1 of observing A equal to lambda and probability 0 of observing any other A. Now, the magic is of course going to happen on Bob's side, because here we get delta B lambda if x, y are in 0, 0, 0, 1, 1, 0. I'm again using this kind of concatenation notation that x, y is now treated as somehow these two numbers mashed together, and if x is 0 and y is 0, then that's this case and so on. And this delta B lambda just means return the value of lambda with probability 1. In the last case, if x and y is equal to 1, we do this, 1 minus delta b lambda, which is just a very cryptic way of saying that if lambda is 0, return 1, and if lambda is 1, return 0. Why? Because if b and lambda are the same, then this Kronecker symbol is equal to 1, and you get probability 0. If they're exactly opposite, and b and lambda both are from the interval 0, 1, then you get 0 here, so with probability 1, you get that outcome, okay? So this just means, in this case, Bob returns exactly the opposite of lambda. So what's the result? What's going to be the CHSH violation of this? Well, of this. So we have the correlation in the XX, or no, in the 0, 0, in the 0, 1, in the 1, 0, minus 1, 1. This was the CHSH, right? With these brackets around, because they are reasonable mean values. Now, what is the correlation in the 0, 0 case? Alice is always returning the value of lambda, and Bob is always, we're in this case, so Bob is always returning the value of lambda. So with probability 1/2, they both return 0, and with probability 1/2, they both return 1, which is like perfect correlation. So this thing is going to be exactly 1. This one, same. This one, same. And now what do we have here? Alice will always return lambda, but in this case, so now this branch gets activated. And in this case, Bob is returning exactly the opposite of lambda. So if lambda is equal to 0, Alice returns 0, but Bob returns 1, which is exactly the opposite of 0. And if lambda is 1, Alice returns 1, Bob returns 0. So they return perfectly the opposite things, you know? So they're perfectly anti-correlated. So the correlation is -1. And that we get 4. And voila, we now have a PR box. So in this way, we can even get higher violation than what we can get with quantum theory. Now, what's the solution? How would you solve this problem? Yeah?
Take the setting just before measurement.
Okay. And how fast do we need to do that? What's the cutoff? You know, like what's just before, like, I don't know, microseconds, picoseconds, milliseconds?
Faster than the light distance.
Yeah. Change before. Is that sufficient? So I think what they did in the 80s was that they had some distance of, I don't know, 6 meters or what, between the measurement devices, and they would, the light speed then would be maybe 40 nanoseconds, and they would change measurement settings there and back every 20 nanoseconds or something like that. And this was then later, this was an interesting and marvelous experiment. Everybody was happy, but this was then later criticized that that's not, strictly speaking, sufficient. Why would that be? Yeah?
Because they need to choose the setting also at that time.
Yeah, because they were actually switching the settings there and back on like a pre-programmed fashion. You know, they had some kind of oscillator that would be switching the settings there and back. But in principle, we can then also introduce the memory loophole, saying that, well, maybe maybe the measurement device remembers what happened in the last round of the experiment, because, you know, you are measuring with the same experimental device again and again and again and again. So while the photon or the photon pair is always different, the two measurement devices are not the same. You cannot nuke your whole setup after measuring one photon pair. And so they can say like, well, maybe it remembers what happens in the last time and so on, and it can somehow adapt once it starts seeing some kind of inconsistencies. So the second thing, which is like a memory, here people call memory loophole, comes into action, which I don't want to discuss too much explicitly, is that maybe the device can remember what happened before, and thus it can adapt to that. And so we need to choose measurement settings randomly. And of course, here comes the question, can we actually choose them randomly? And there comes the problems with superdeterminism, that if everything is predetermined, even the way we choose the measurements, we cannot choose them randomly, and all of this becomes a huge problem. Of course, then people usually tell you that, well, if we cannot choose them randomly, we have no free will and we cannot actually do physics, so we're not going to discuss that one case. You can internally solve this problem the way you like. Another thing, another loophole, which is way more relevant for theory, is the post-selection loophole. And this is actually an interesting one. Because it turns out that when you're doing an experiment, what you do is that you have detectors which try to detect photons, okay? So for example, you have a photon traveling somewhere along a path, and then you put some kind of beam splitter in there, and the horizontal polarization goes this way, and the vertical polarization go this way, put in a mirror, and then you have a detector here and a detector here, okay? And in principle, if the photon comes and it has horizontal polarization, this one clicks, and if it has vertical polarization, this one clicks. If it has some kind of superposition of those two, it somehow follows one or the other path in superposition, and then one of the detectors will click because somehow the superposition will collapse into a convex combination or into just the diagonal part of the density matrix. Now, in principle, both detectors cannot click because there's not enough energy in the system to make them both click. Although this can happen because you can have stray photons in your lab, you know, like usually if you have a lab, it's not ideally isolated from outside influence, and there's like sun outside, and there can be like a little gap in your window where some light shines in and a stray photon can run into your detector, and both of them can click in principle. But a bigger problem is that none of the detectors have to click, because what they're trying to do is detect single photon, which is like kind of these kind of dominoes, you know. So the photon is going to like hit a small domino, which is going to hit a bigger domino, which is going to hit a bigger domino, and so on. But this can actually go wrong, and nothing can click. So what can happen is that we can have no click events when none of the detectors clicks. This can be either because of detector efficiency or because maybe the photon got lost, you know? Like the waveguide is not of zero width, it's something like a tube, and we want the photon to travel like along the tube, but sometimes it can start bouncing around, and then it can basically tunnel outside of the tube, or, you know, just get lost. You have some kind of you know, also the mirrors and everything. Stuff happens. So the question is, what happens in no-click events? So what would be the solution to no-click events?
Into our theoretic description.
Well, yeah, that's the correct solution. What would be the wrong solution? Yes, exactly. So the naive thing to do would be to say that, okay, if Alice or Bob gets a no-click event, just don't count those rounds, okay? So in this case, what would happen is that our probability distribution would be subnormalized, so we would have something like sum over AB, P, AB given XY strictly less than 1, because we have dropped some kind of events, so we can renormalize the probability distribution to count, to sum up exactly to 1. Or that just basically means, like, if you have something like a Excel sheet with all of your results of all of the runs, you would just delete the rows where you would have no-click events. And this is called post-selection, because after the experiments, we are just selecting some of the data from our statistics, and here we would be selecting the data that do not have no-click events. Okay. Now, we need to do an example showing that this is the wrong thing to do. Maybe I have to start writing here. So now what will happen is that these PAB given X lambda, they can either return probability or they can return a no-click, okay? So we'll have like a new thing that they can do. And what we now do is that the hidden variable would be ordered triple of X, Y, and AB, okay? So now you should see this as a multi-index. this whole vector is like one lambda, okay? It's not going to be a number, it's going to be a vector. And x, y, a, b are both in 0, 1. And now what we do is that for x, y in 0, 0, 0, 1, 1, 0, we can have that probability of x, y, a, b is 1/8 if a, b are in 0, 0, 1, 1 and 0 otherwise. And for x, y equal 1, 1, we have that p of x, y, a, b is 1/8 if a, b are in 0, 1, 1, 0, and 0 otherwise. Now, these are the response functions, so don't remember this is the lambda now, okay? This whole thing is what we had before as lambda, and since we have x and y and a and b here, I'm going to be using a prime and x prime here, because otherwise I would have a twice and they don't have to be the same thing. And here we return delta a prime, so we exactly return a here as a prime if x is equal x prime and no click otherwise. And the same thing happens in Bob's detector. We return delta b prime if y is equal to y prime and no click otherwise. What's the probability that we return something?
For each one 1/2 and together 1/4.
Yes. Right? So if I fix any value of x, then x prime is either exactly equal or exactly opposite, because they both are either 0 or 1. So this happens in 50% of cases, and this in 50%. So here we have 50%, and here we have 50%. Okay? Altogether, we have 75% chance of no click, 25% chance of click on both sides. So what happens in those cases where both detectors click? So if we choose x and y to be one of these three settings, and both detectors click, then we get exactly the same outcome, because it's either both zeros or both ones with some kind of probability, or we get that and nothing else. And if we set x equals 1 and y equals 1, we get exactly the opposite things, okay? So in those 25% cases, if you would look just at those data, post-selected, you would get, in this case, perfectly correlated outputs, and in this case, perfectly anti-correlated, so you would get a PR box and SH violation of 4. But that's only if you restrict to the 25% of cases where both detectors click. In the other 75% of cases, which one would want to drop, but this clearly shows that we cannot, one would get something completely different, because then we would have to somehow say, what should we do with this no-click event? And that's exactly the solution to this problem, that we should see the no-click event as some kind of event in itself. So we should not have just 2 measurement outcomes, we should have 3 measurement outcomes, which is like horizontal polarization, vertical polarization, and no-click. And then one can, in principle, have many solutions. You can say that during a no-click, I'll just generate a random number, I generate a random outcome. I'll assign no clicks to horizontal polarization, for example, and add those 2 outcomes. Or you can just say, okay, now I have 2 measurements with 3 outcomes each. And in this way, we can actually get rid of this, because we will not be post-selecting any data. We'll just be treating all of our data as one huge sample. This post-selection loophole is especially important because even in theoretical analysis, you can do this. So this locality loophole is somehow it's somehow hard to do this as a mistake if you are doing some calculations, but in the post-selection loophole, it's kind of easy to say like, oh, by the way, if I just restrict to this data, or if I just drop these parts of what I'm doing, then I get some interesting results. Well, yes, because you're doing post-selection. Also, another way to see what's going on here, or how I wrote this down, is that when the particles are being initialized, what they do is that they create a local hidden variable lambda, and it tries to guess the inputs x of Alice and y of Bob. And if they guess correctly, they return the correct outcome, and if they guess incorrectly, they return no click. Okay, so somehow you can see that this post-selection can be either seen as guessing and not returning anything if you guess wrong, or you can also see this as a form of communication, because in principle you can say that one way to communicate with someone is to send them a random message, and if I later realize that that's not what I wanted to say, I'll just say like, never mind that. So in this sense, you can also somehow map post-selection to communication, because you can say, well, like, it's like if they would be communicating, except for if they don't communicate the correct things to each other, then they just abort, which is the no-click event. Now we can get to something actually more interesting and more mathematical. Who of you heard about the MIP star equals RE? So the way we did Bell experiments previously was that we had a state rho AB, which was a density matrix on Alice and Bob. And we have measurements on Alice, measurements on Bob, and we did PAB given XY is trace rho AB and now I'm going to rewrite this in a very trivial way, because I can see this as a product of two operators. One is MAX tensor identity and the other one is identity tensor NPY. And I can call this M tilde A given X, and I can call this N tilde B given Y. And now something you can easily check is that these things commute. There's a question that we can now ask, is whether tensor products are the correct thing to describe two parties. You know, because for example, in field theory, in some of these things, we don't have like when we have spatially separated things, they might not be described by tensor products of something like local Hilbert spaces, but they might be described by commuting sets of operators. So in other words, we can say that doing the experiment in this way we can call this the entanglement strategy. But we can also say that, well, maybe we can actually measure violations of Bell inequalities in a bit different setting, which would be the commuting measurement strategy. Which we shall say that, hey, just take a density matrix on a single Hilbert space, so now we have just one. And take P of EMs MAX and NBY, such that for all AXBY, we have that this commutes with that. And then the behavior is just this thing. It's not even clear that this is positive, that this is a positive number in general, but it is because if they commute, what I can do is that I can write ma given x as square root of ma given x times square root of ma given x. And if ma given x commutes with nby, then also the square root of it commutes with that. Now I can switch these two. And now I argue that this is a positive semi-definite operator. Which is true because if I put here psi ma given x and b given y, ma given x is a square root, then this is something like phi and by phi, where this phi is. So we let this act on that vector and this act on this vector. This is again one of the places where one would appreciate the mathematical way of writing inner products, because while calling this phi is kind of easy, but putting the ma given x to act on this vector, well, you either write it before this psi into this bracket, but then you have to know what you mean, and it's in principle not entirely correct, or you just somehow bracket it like this. Well, you know, the mathematical way of writing inner products is that what we write, for example, like this, they would write like this, but then also acting window operator on here is a bit more well-defined. On the other hand, it's really hard to write something like this type of projectors in that notation, so nothing is perfect. I'm going to now talk very hand-wavy, so what I'm going to say can be put into a rigorous mathematics, and if you want, I can give you references for that or papers summarizing all of these results, but now I'm just going to be very hand-wavy to somehow explain the problem, or somehow a current problem that we have now with these two things that we can do. So CQ is going to be the set of all behaviors obtainable with entanglement strategies. CQA will be the closure of CQ. So a topological closure, if you would restrict this to behaviors of a fixed size, then they live in a finite dimensional vector space, and the closure is obvious. And CQC are the behaviors obtainable with commuting measurement strategies. What is the burning question? Yeah?
Is the equality?
Yes. So what we would want to know is whether CQA is equal to CQC. Now, this is, if that's the case, then we cannot tell apart the tensor product of Hilbert spaces to performing commuting measurements, which would somehow justify that we can just describe everything in Bell experiments with tensor products. And yeah, would somehow answer some questions about how to maybe talk about different measurements in field theory and other stuff like that. Now, and this is actually an old question, and many people worked on that. Among them, Boris Cyrelson, who was really interested in this problem. And we have some results. So if the underlying Hilbert spaces, so if the dimension of H is less than infinity, So it's fine. So everything is finite dimensional, or Alice or Bob, not slash Bob, but Alice or Bob, doesn't matter which one of them, perform two dichotomic measurements. So two dichotomic measurements means two inputs, two outputs, two measurements with two outcomes each. Then CQA is equal to CQC. Which is kind of nice because that would hint towards equality holding in the most general case. But interestingly enough, in 2020, there was a paper called MIP star equals RE, which proves that this is not the case. And not all infinite-dimensional commuting measurement strategies can be approximated, because you have to understand there's a separation between this set and the closure of what we can do with entanglement strategies, which means that so somehow if we would prove that CQC is not the same as CQ, then one can say that, okay, maybe there are some things that we cannot exactly obtain with entanglement strategies, but maybe we can at least get epsilon close for arbitrary small epsilon by, for example, taking bigger and bigger Hilbert spaces and so on. But this is inequality between the closure of what we can do with entanglement strategies and this set, which means that it somehow looks like this, that this is CQA and the whole thing is CQC, and there's something like a non-trivial part where one stops and the other one continues. So the entanglement strategies cannot even approximate everything that we can do with commuting measurement strategies. And now it's unknown whether we can actually find experiments. Okay, this means that there must exist some kind of Bell inequality. So this would be some Bell inequality, which has some kind of upper bound, say 1 on the closure of entanglement strategies, but has upper bound 2 on the set of commuting strategies, or say some other numbers than 1 and 2, maybe A and C here, or whatever you like. But this is just an existence proof that we have. We know that such Bell inequality must exist. We don't know what it is. We don't even know how to find it. We don't know how to approximate it. We don't know anything. And the problem why that is the case is because we have no kind of proper ways to estimate what is in this set or what is inside of this set. So we have no kind of we have no sufficient approximations for these sets. We somehow know that they exist, that they're closed, but it's really hard to determine what is in what and to find this Bell inequality and to propose experiments that would measure it and try to violate it beyond this bound in some kind of experiment with commuting strategies and so on. So finding such a Bell inequality is a big open problem, and probably very hard one, because this paper, it has like 250 or 270 pages. But it also disproves this embedding theorem for von Neumann algebras, and it's like a big piece of mathematics and very connected between quantum information and computer science and theory of operator algebra. So it's a hard paper to read, but I would say it's assumed to be correct in the community. So such Bell inequality must exist, and now the goal is to find it. Now, actually, the only thing that we know about these sets is how to get outer approximations of this CQC, okay? So what outer approximation means is that if you take the set of CQC, then we have some kind of hierarchy of outer approximations, so that we can say that for k equals to 1, this is the outer approximation, okay? So if you try to, and maybe here would be the PR box. All right, okay. I don't know if PR box is already ruled by the first level of this hierarchy, but you can imagine it is. And there would be some kind of more and more approximations that get ever and ever tighter to CQC, okay? Which means that the only thing that we know about these two sets is that there exists a hierarchy of outer approximation for this set, and also there are some no-go theorems why there cannot exist hierarchies for some other approximations of these two sets. Now, this hierarchy for the outer approximation of the CQC set, this is what we call the NPA hierarchy, named after Navascues, Pironio, Assim, and this is what I'm going to try to explain to you now, very shortly. This is going to be just like a very short introduction to that one, and I don't really want to go too deep into it, but nevertheless, it should expose you to that hierarchy. Today, we can just try to prove a supporting lemma that we will need to formulate the NPA hierarchy, and I'll explain the NPA hierarchy on the 14th of January, because I want to make I don't want to cut myself off in the middle of trying to explain it, because then it will probably be not very clear, and I would really like you to at least have a rough idea of how the NPA works or how to write it down, because it turns out that while getting the outer approximations of the set of commuting measurement strategies is a rather theoretical and foundational problem, one can still use this to get outer approximation of behaviors that are reachable in quantum theory, which has some applications in quantum key distribution, but also what one can do is one can take the idea of the NPA hierarchy and transform it to other problems where you're dealing with similar situation and still get some kind of semi-definite programming problems that can tell you something, that can give you some upper bounds and so on. Okay, so today we will just prove the following lemma. Let S1 to Sn in LH, so just some operators, and let U be a vector in the same Hilbert space. So we have n operators indexed by an ordered index n and a vector. We can define the numbers Rij as U, Si star, Sj, U, okay? And we can define the matrix R, which is going to be the matrix with those coefficients. Okay, so for example, this can be of the form U, S1, S1, U, U, S1 star, S2, U, U, S2 star, S1, U. So this is the row index, this is the column index. U, S2 star, S2, U. Of course, here we can have n operators. This is just example for n equals 2. Now, another way to see this matrix is that I can define vectors Vi, which are of the form Si acting on U, and then Rij is just the matrix of the inner products of, Vi and Vj, okay? So again, what I'm doing is that this operator acts here, that operator acts over there. And this is called the Gram matrix. This is just a mathematical term that you can, again, Google or look for in textbooks if you need to know more about these matrices. Okay, this is just a definition. And now we want to prove that then this matrix is positive semi-definite. Yeah?
One way would be to multiply it from left and right with the same vector and assert that it's positive.
Yes, exactly. So we said that we have an operator on the Hilbert space H, or let's call it, because we already used H there, K. And we had that A is positive semi-definite if and only if psi is bigger than or equal to 0 for all psi in the vector space K, right? And this is like a reminder of what that means. Now, I don't want to use the same notation for the inner product as I used here, otherwise it would be like a bloody mess, okay? Or to put it differently, one way to do this would be to say that R is equal to sum over ij, Rij, ij, and then you can use this inner product. Or the other way to do it would be to use completely different inner product. So I'll use the inner product that you would usually see in like linear algebra in high school, or the one I saw in high school. I don't know what you saw in high school. But I'll just say that alpha is a vector of alpha 1 to alpha n belongs to c to the power of n. So it's a complex vector space of dimension n with the natural inner product that we have there by multiplying row and a column. And then what we can do is that we can do this kind of alpha star times r times alpha, or basically this inner product. Now, these are round brackets because this is the high school inner product, which when expanded in coefficients is alpha I prime. It's coming from this one. Don't remember we are complex. It's complex conjugated Rij alpha j. So this is what you meant, right? Yep.
Use the definition of Rij.
If you're stuck in a proof, look at what you were given in the lemma and try to see whether you can plug something somewhere. It doesn't work always, but sometimes it works, and this is the sometimes. So we plug in that thing. But the sum over I just happens only here and here, and the sum over j just happens only here and here, so I can pull all of those things together. Now, I have essentially switched the order of the inner products, because what we are doing here is that we are doing inner product with a matrix in the middle that itself is constructed out of inner products. And now we have switched the inner product, that the outer inner product is the inner product on that Hilbert space H, and here inside we have sums of operators and vectors, okay? That's why it's important at least personally to me, to denote this inner product and that inner product completely differently. Otherwise, it's very easy to get confused. Now, this is a sum of adjoint operators and complex conjugated numbers, so I can somehow pull out the star from the bracket. And this is where the magic happens, because inside of here we have some operator S alpha, and inside of here we have the same operator S alpha. Just the index is called something different. Now, for the sake of completeness, we can again say that this is some kind of vector, say, let's call it phi alpha, and this is phi alpha this way. So what we are making is that this S alpha operator will act on this U, and this S alpha star will act on the, in this way. So again, if we would have this type of inner product, we can just pop it in that direction and star it. But this is really hard to write down in the bracket notation, so we'll just denote it like that. And so we get phi alpha here and phi alpha here. Okay, and why is this positive number? It's norm squared. But yeah. So the main idea in NPA hierarchy would be that we will assume that we have some kind of density matrix, or in general, we can just assume the density matrix corresponds to a pure state, so we'll have some kind of vector that will be the vector U, and that we have some kind of projectors. In general, we should take P of EMs, but then we can somehow reduce this only to the case of projective measurements. So those projective measurements will be those operators S1 and Sn, and somehow we will construct those operators out of them. And we'll get some kind of Gram matrix of the form R. And thanks to this lemma, we will know that that matrix must be positive semi-definite. Plus, we will get some other constraints for things in this matrix that will correspond to the behavior we're investigating to see whether it can be obtained from commuting measurement strategy or not. And in this way, we'll start getting an SDP hierarchy. And this is called the NPA hierarchy to determine that.